Thank you for joining us today. At the end of this session, I hope you'll come away with a better understanding of scope specifications and what kind of features are available in today's instruments. This session is geared towards choosing a scope for your bench, when and where you'll likely be doing most, if not all of the research on your own. If you're considering a scope with a bandwidth above 1 gigahertz or for a special purpose testing application, you should probably talk to an application engineer at Tektronix to help you make the right choice. During the presentation, I'll talk about the specifications that determine the signals a scope can measure. Secondly, we'll cover the latest features that can save you time or let you do things that you couldn't otherwise do, like finding intermittent anomalies or supporting specific standards or applications. And lastly, we'll talk briefly about environmental factors like portability, data transfer, and remote control. Through the session, you'll hear me refer to terms like basic scopes, mid-range or bench scopes, and high-performance scopes. On this slide, I try to give you a rough idea of what I mean by these terms. Note that the scales on this chart are sort of pseudo-logarithmic in order to fit in all the bandwidths and prices. The slide is meant as a guide, strictly that the performance realm goes much higher than 20 gigahertz, and it also may go higher than $200,000. In this section, we'll be talking mainly about specifications and how they're defined and applied. As we talk about scope specifications, you'll find that you'll need to have a pretty good understanding of what signals you're going to need to look at. Are you looking at mainly audio signals? Are you looking at mostly digital signals, transducer outputs? If you're looking at digital signals, are you going to be evaluating rise times or just looking at approximate timing relationships? Are you looking to use the scope to qualify key elements of your design, or are you using the scope mainly as a debugging tool? Does your module include a wireless component, or do you need to test in the frequency domain? In any event, you need to do some soul searching and consider all of these factors before you start looking at specifications. One of the first, and perhaps most obvious thing to consider is how many and what kind of channels you're going to need. Except for some very basic hobbyist entry-level scopes, most oscilloscopes have 2 or more analog channels to allow you to compare the timing of signals. The analog channels have to be designed for really good range of linearity, gain, accuracy, and flatness, and at the same time have some reasonable robustness. By that I mean mainly electrical robustness, in that they can't break every time you connect a cable after shuffling across the floor on a dry day. Most of the scopes out there today are digital storage oscilloscopes, so that the analog channels are sampled to provide data for storage and display. In general, the more channels the better, but since many of the critical components on an oscilloscope are in the analog front end and within the sampling system, adding channels add to the price tag of your oscilloscope. A mixed signal oscilloscope, or MSO, adds digital timing channels which indicate high or low states. Since these channels are often used to work on computer-based systems, digital channels come in bite-sized, that's BYTE, bite-sized chunks of either 8 or 16 bits. Tektronix pioneered the concept of a mixed domain oscilloscope, or MDO. These instruments include the same analog and digital channels as the MSO, but they also add an RF input channel that behaves almost like a spectrum analyzer. With the advent of wireless on almost every design, engineers have the need to ensure functionality of their embedded designs in very different ways. They now need to make basic and maybe advanced RF measurements to ensure devices turn on, validate RF transmit and receive functionality, as well as troubleshoot for things such as EMI and/or Wi-Fi compliance for the devices under test. Having a spectrum analyzer within an oscilloscope fulfills this need and also saves a ton of bench space due to integrated instrumentation. Bandwidth is one of the key specifications that determine how a scope relates to the signals you want to look at. Scope specs usually represent the bandwidth in two ways, either as the -3 dB frequency at the high end of the bandwidth or as a scope rise time. The two specifications are related. First, we'll talk about the usual way of specifying bandwidth. All oscilloscopes have a low-pass frequency response that rolls off at higher frequencies. Oscilloscope bandwidth is specified like a simple low-pass RC filter. That is, we specify the bandwidth using the frequency where a sinusoidal signal is attenuated to 70.7% of its true amplitude. This is the -3D point or half power point. And the same as with a low-pass filter, we assume that the input is a pure sinusoid. What you see here in the slide is a typical log-log frequency response plot for a 1 gigahertz oscilloscope, including the characteristic roll-off and specified -3 dB point. One of the things you'll notice right away is that the bandwidth spec, the scope can be roughly 30% low. You can tell that this is important because I've made it in red and put an exclamation point after it. You also notice that at 1/5 of the bandwidth spec, the response is pretty flat, and the error due to roll-off is relatively small at around 2%. Pay attention to this last point because it's going to come up again as and when we talk about the first rule of 5. In addition to understanding the concept of scope bandwidth, it's important to have a good understanding of the frequency components that go into your signals. If you're dealing exclusively with sine waves, then life is pretty simple. The highest frequency you're dealing with is the highest frequency of the sine wave you work with. However, if you're like most of us, you're going to be looking at signals like square waves or rectified sine waves, pulse or transducer output signals. For signals like these, it's important to remember that the highest frequency of interest, much higher than the repetition rate of the signal. As you probably remember, non-sinusoidal signals can be built by overlaying a series of sine waves of different amplitudes and frequencies. These different sine waves make up the spectrum of the signal, and it's important to consider if you want to get an accurate representation of these signals. This slide shows how a digital signal, really a square wave, is made up of a fundamental frequency, third harmonic, fifth harmonic, and so on. At least the first few harmonics must be captured to get a true representation of the square wave. If the scope bandwidth excludes the harmonics, you will lose the shape of your waveform. You'll notice that as I add even higher harmonics, the edges get even steeper. This shows the relationship between a bandwidth and rise time. I will talk more about rise time in just a few minutes. In general, a higher bandwidth will provide a more accurate representation of the signal you have in interest. Remember when I showed the roll-off of a typical scope? I said that the response was pretty flat until we hit roughly the 1/5 point of the bandwidth, while the actual roll-off of an oscilloscope can vary from scope design to scope design. This 1/5 relationship is a pretty good rule of thumb. So to determine the oscilloscope bandwidth you need to accurately characterize signal amplitude, please follow the 5 times rule. By that, if you choose your scope to have 5 times the bandwidth of your signal, you should expect less than a plus or minus 2% error due to roll-off. For example, if you're working with a 20 megahertz sinusoid, you'll want to choose a 100 megahertz oscilloscope to get accurate amplitudes. This slide shows how bandwidth is presented on a scope data sheet. For those who work with digital signals, it's often easier to think in terms of rise time. This slide shows the effect of capturing a signal with about 1 nanosecond rise time at 3 different bandwidths. To illustrate the relationship between bandwidth and rise time, we captured the signal on a high-performance oscilloscope that has a variable filter capability on its input. The time scale here is 4 nanoseconds per division. What you'll notice that at the 500 megahertz bandwidth, the edge is slowed down quite a bit. As the equation on the slide suggests, the rise time you see is the combination of the actual rise time of the signal and the rise time of the oscilloscope. So at 500 megahertz, the scope adds slope that isn't part of the frequency components of the signal being attenuated. At 2 gigahertz bandwidth, the waveform is truer to the actual input signal. And at 8 gigahertz bandwidth, the waveform shows even more detail. But at this point, you need to decide whether the detail is that important enough to justify the price tag of an oscilloscope with said 8 gigahertz bandwidth. So higher bandwidth oscilloscopes will be able to more accurately display faster rise time. Just as with bandwidth, we have to account for the roll-off characteristics. Again, we use a rule of 5 as shown on this slide. As example, to look at a 4 nanosecond rise time, we would need a scope with a rise time 5 times faster than 4 nanoseconds, or, in other words, 800 picoseconds or less. Sample rates is an important specification because most scopes today are digital sampling oscilloscopes. By that, they convert analog signals into digital values, and the rate at which they do it is the sampling rate. It's given in samples per second. In general, the faster the scope can sample, the less information you'll lose, and the better the scope will be able to represent the signals under test. But the faster you sample, the faster you'll fill up your memory, so this limits the amount of time you can capture. The specification given in the datasheet is almost always a maximum. So to balance sample rate and recording time, digital oscilloscopes change their sampling rates with the horizontal scale. Oscilloscope designers try to keep a certain number of samples per division to make sure you get good resolution for all horizontal scale settings. You probably need to flip through the manuals, but you can often find a table that shows the sample rate for each time per division setting. Some instruments will share the sampling systems between channels to save some money. This means that the number of channels you turn on can affect your sampling rate. Whether or not the sampling rate changes with the number of channels turned on is usually shown as a footnote on the specification datasheet. In order to avoid aliasing, the Nyquist theorem tells us that the signal must be sampled at least twice as fast as its highest frequency component. This rule of twice the maximum frequency should be viewed as an absolute minimum that will prevent gross distortion. Remember, the highest frequency component of your signal is often much higher than the repetition rate of your signal. And it's a good idea to be able to have visibility of higher frequencies to see the details. At the fast time scaling setting, the scope will interpole between samples to fill in the trace. Most Tektronix oscilloscopes use a sin x divided by x function to fill in the spaces between the samples. This type of interpolation is optimized for sinusoidal waveforms. which from our discussion of bandwidth and from school, we know are the basic building blocks of complex signals. Linear interpolation is simpler, but not as good for representing sine waves. The graph on this slide shows the difficulty of using straight lines to build a sine wave. If the scope uses linear interpolation, it's going to need faster sample rate to accurately draw a sine wave. Tektronix recommends another rule of 5 here. We suggest your sample rate should be 5 times faster than the highest frequency component of interest. This will give good detail and is more than enough to fill and avoid aliasing. Most of the scopes maintain this relationship, and as an example, I've clipped the datasheet for a 500 megahertz oscilloscope. The fastest sampling rate of 2.5 gigasamples per second allow you to capture 5 samples of each cycle of a 500 megahertz sine wave. Record length is the number of samples the oscilloscope can digitize and store in a single acquisition. Since an oscilloscope can store only a number of samples, the waveform duration or length of time captured will be inversely proportional to the oscilloscope sample rate. This relationship is shown above in the equation and in the example datasheet. Longer record length combined with faster sampling rate helps you get more detail. But please remember, when you're using a digital oscilloscope, you can usually increase the sample rate by using a faster time scale up to its maximum. But faster sample rates eat up memory faster, so you'll need longer record length to acquire the more samples. Just as an aside, since we're talking about billions of samples per second, adding longer record length isn't just a matter of popping on a couple of more RAM chips. The whole sampling system has to be carefully designed and scaled to deal with the memory while maintaining very tight timing specifications. The most basic reason for trigger function on an oscilloscope is to allow you to stabilize the trace which is on the display. The oscilloscope's trigger function synchronizes the horizontal sweep at a specific point on the signal, and the trigger control sets that point. This is especially important for analog oscilloscopes that cannot store individual traces. With an unstable trigger, the signal becomes jumbled on the screen since the drawing begins at a different part of the waveform each time. This is the picture on the right. The most basic trigger circuit is the edge trigger, and all oscilloscopes have this capability. Pulse width triggering is also available on most oscilloscopes, and most scopes include special provisions for triggering on video signals, since they are complicated and can be challenging to stabilize otherwise. A singular trigger causes acquisition on all input channels simultaneously so that the signals are all time correlated. This is true even when the oscilloscope includes digital and serial signals or RF signals. Now let's begin talking about some of the more advanced features and time savers that are available today. I've already covered basic triggering as a way to get a stable display, but today's oscilloscopes go way beyond this. They also are to provide tools to help you zero in on really specific parts of a complex waveform and allow you to capture anomalies like run pulses, setup and hold violations, as well as narrow glitches. For years now, some oscilloscopes have been able to trigger on combination of inputs. What we call logic triggering allows you, for example, to tell the oscilloscope to trigger when all channels simultaneously show a logic high. More recently, oscilloscopes are able to trigger on serial data as it occurs on the input channels. So, for example, you can tell the oscilloscope to trigger when it sees an ASCII question mark on an RS-232 serial bus. I'll talk more about serial bus options shortly. The list here on the slide is just a sample of some of the advanced triggers, and unfortunately we don't have time to go into all of them, but maybe we'll do a follow-up session if the demand and feedback is there. There are more and more triggers available on higher performing scopes. User manuals are a good source of information on the latest triggering alternatives. With today's long record lengths, search tools have become almost as important as trigger tools. Capturing an anomaly is only a good first step. Once you catch it, you still have to find it in the scope's memory. You'll want to check out this capability, especially if you're leaning towards an oscilloscope with a record length of millions of samples. Many Tektronix oscilloscopes include a neat facilitation called Wave Inspector. This is to help you navigate through very long records. It is made up of dedicated controls on the front panel to allow you to quickly search, pan, as well as zoom. I can't spend a whole lot of time on this topic, but please check out the demos that are on our website at tek.com. You can see the results of a search above. The hits are indicated by white triangles in both the acquisition overview and in zoomed view on the slide. Wave Inspector duplicates most of the trigger functions as search functions. So for example, you can trigger on a pulse that is higher than 1 volt for less than 10 nanoseconds. Then you can use that same criteria to search for similar pulses to see how many you have captured and get an idea of how often the glitch is occurring. Capture rate can be seen as both a hard specification as well as an advanced feature. So in the end, I've decided to keep capture rate and digital phosphor together as a topic. Capturing intermediate events is an exercise in probability. So imagine that I'm trying to take a picture of someone blinking with my camera. Now, what you need to know about my digital pocket camera is that it has a very long cycle time. Because of that latency between snapshots, I can only capture someone blinking by sheer luck. You can also imagine that if I had a much faster camera, I probably would have a better chance at catching the blinking. This is illustrated with the upper graphic on the slide, as we try unsuccessfully to capture an infrequent runt pulse on an oscilloscope that has a slow waveform capture rate and successfully on a scope that has a much faster rate. So waveform capture rate tells you how fast the instrument can acquire, store, and display data. It also gives you a sense of how likely it will be for you to capture infrequent events. Now, in addition to being able to capture waveforms, the instrument needs to be able to display the information in a way that makes sense. Just because a scope can capture thousands of waveforms per second doesn't mean our eyes can see them all. Some oscilloscopes have the ability to use intensity grading to represent how often an event occurs. Infrequent events appear dim and frequent events appear brighter. Because it looks like the phosphor on an analog CRT, Tektronix calls this function digital phosphor. And you'll find it on Tektronix scopes from our basic bench models to our higher performing and higher performance lab instruments. The lower picture on the slide shows how a digital signal varies in time relative to the trigger, which is on the left-hand side of the screen. You can see by the intensity that the rising edge spends most of its time in the center of the screen, but moves over about 4 divisions. And occasionally the edge happens even sooner. Most designs today are using serial bus for interchip or module-to-module communication. These have traditionally been tough to troubleshoot on oscilloscopes just by the virtue of their serial nature. But with longer record lengths and more processing power, some oscilloscopes are able to decode serial buses and use the decoded information for triggering and searching. Some buses, especially really common intermodule buses like RS-232 and USB 2.0, they can be decoded by relatively cheap bus sniffers. The difference between the scope approach and the standalone bus decoders is that the oscilloscope approach allows you to look at any related signals on a time-correlated display, which allows you to see how many bus commands sync up with other events in your system. In fact, our MSO 5000, DPO 7000, and 7K higher performance oscilloscope offers serial triggering and decode for super speed USB 3.0 signals. This slide shows a table taken from the Tektronix DPO 3000 series datasheet. It shows how serial buses are bundled together as options and what functions are supported in each serial bus. We haven't talked about event tables, but this lets you see a list of the decoding bus states on the scope display. If you work with serial buses, make sure that you check out the scope's datasheet to see what's available for the specific model you are considering. Now I'm going to cover a number of analysis features in this next sequence. Depending on how important these features are to you, you may want to spend more or less time researching them. I'll touch on each one very quickly and try to give you a sense of how common each one is. Cursors are often in most scopes today, and most scopes allow you to use them to pick off values off the vertical or horizontal axes. The cursors shown on the slide automatically indicate the waveform value at the cursor position. The ability to add and subtract channel waveforms have been around for a very long time, and most oscilloscopes have some capability in this regard. At the very least, you will want to be able to subtract the channels to make pseudo-differential measurements. It's also very common that you will want to multiply channels together to get power. The range of math capabilities go from this kind of simple function all the way to being able to enter complex expressions with constants, calculus, as well as trig functions. You may be able to get some sense of the math capabilities for your scope from the datasheet, but if this is really important to you, I'd recommend that you download some of the user manuals and take a look through them to see what is doable and what is not. Automatic waveform measurements let you take numerical readings based on the waveform. Some form of automatic measurements is available on most scopes, but the range of capabilities vary quite a lot. Measurements often include time-related parameters such as pulse width, period, frequency, rise time, amplitude, related parameters like min or max voltage, peak-to-peak or RMS voltage. Some oscilloscopes can give statistical measurements like histograms or even jitter and eye pattern measurements. One way scopes can distinguish themselves is how flexible they are to gate and make the measurements. Does the measurements happen over the whole record length or just over the display or just between the cursors? On some instruments, you can actually set these. You can also see from the example on the slide that you can get statistics like mean and min for measurements. Max and standard deviations are also available but are hidden in this example. The user manual, again, is probably the best place to learn about automatic measurements. Limit testing and mask testing are similar, so allow me to cover them at the same time. Limit testing is not universally available on all scopes because not everyone does this kind of testing, and it takes some considerable time for setup. It can be very useful, though, in pass-fail testing, qualification, and manufacturing environments. The limit test software compares a signal under test to a known good or golden version of the signal with the user-defined vertical and horizontal tolerances. Mask testing is also used, and somewhat more narrowly, so it's generally an option and not a standard feature. It usually is checked and used for checking telecommunication and data transfer signals for compliance to a standard like ITU-T, Ethernet, USB, or other standards. If you are interested in this type of testing for general purpose use as opposed to compliance testing, you may also want to look at the visual triggering function that's available on our DPO 5000 or higher series oscilloscopes. This visual triggering allows you to draw shapes on the display and have the scope trigger whenever the signal moves in or out of the shape you've drawn. It's designed much more for general purpose triggering in this regard. Many oscilloscopes offer a fast Fourier function, or FFT, that allows you to look at the frequency spectrum on your signals. If this is important to you in your work, you may want to spend some time understanding how this FFT operates on the oscilloscope. There are a few things to look at. 1. What information does the FFT give you on the screen? On the screen example above, you'll notice that the vertical and horizontal scales, as well as the recording length and sample rate. These are all good to know when you're evaluating your FFT. Second, you'll definitely want to use cursors on the FFT display. Most scopes support this. Third and lastly, you'll try to find out how and what memory that the FFT will operate on. Ideally, the FFT should use the full memory of the oscilloscope to get the best frequency resolution. Performing FFT only on the display memory makes the display update quickly, but you lose frequency resolution. If you're going to be doing a lot of RF work, then you might want to consider a mixed domain oscilloscope, or MDO. They have a dedicated RF input and spectrum analysis controls for displaying signals in the frequency domain. The key words on the slide are time correlated. You can see that what an RF spectrum looks like at the specific time. You can also see the analog as well as digital values at the same time, including serial buses. You can also look at traces of frequency, power, phase changes on the RF channel over time, and relate these to analog and digital signals at other points in your system. It is worth noting that this is a dedicated spectrum analyzer built into the system. It is not an FFT as shown on the previous slide. These MDOs are the only scopes that include a separate RF acquisition system for the spectrum analyzer. So you will not need to compromise on any accuracy of your measurement or any flexibility with regards to adjusting parameters such as reference level, RBW, and so on. If you get into specialized applications, you'll probably want to investigate application software, especially on mid-range and high-performance oscilloscopes. We've already talked about RF applications a bit in reference to the MDO, but if you're working down into the very nitty-gritty of signal integrity for digital communication, you may want to look at scope applications that can demodulate high-speed signals, display the spectrum and spectrograms, and pluck out symbols from the data stream itself. These applications generally make sense only on oscilloscopes with bandwidths in the multiple gigahertz ranges. If you're getting involved in power supply designs or evaluation, you may want to look into power application modules. These allow you to measure specific power parametrics such as harmonics, switching losses, and safe operating areas. These applications are available starting with mid-range oscilloscopes in the 100 megahertz range. Jitter measurements are used to evaluate frequency and phase variations in clock as well as data streams. This type of measurement generally requires really fast sampling rates, high time stability, and long record lengths. So jitter measurements are usually done with the higher end oscilloscopes. In this last section, we'll talk about how a scope fits in your work environment. Very few people fall into the middle when you ask them this question: do you prefer your scope to use a proprietary operating system or run on something like Windows? There are very clear camps on this issue, but one you get beyond all the ranting and raving on one side or the other. The answer can have as much to do with the application as it can do with your passion on the topic. If you're going to do a lot of work with analysis or simulation as you're gathering the signals, you may want to consider going with something like Windows. If you're mainly doing general debugging, well, the operating system question may get back to which camp that you reside in. Tools and techniques for control and data transfer are a topic that could easily fill several more hours. Unfortunately, we do not have the time to touch on that here. But for sake of covering the topic, for transferring data directly to a computer or remotely controlling a scope, you have a number of alternatives. USB is probably the easiest alternative for quick transfers, and it's available on virtually all PCs, and the cabling is foolproof. Ethernet is a close second choice, and while it might take a little bit longer to set up, it has the advantages that many scopes can serve up from a home page like the one shown on this slide. GPIB requires special hardware and fairly expensive cables, so unless you're working on test stands, most people stay away from this option. And RS-232 is rarely seen anymore due to its slower speed and trickier setups than the options above. Most manufacturers offer programs that you can use to grab screens, settings, or waveform data over one or more of the interfaces above. Tektronix calls our utility Open Choice Desktop. If you're on a LabVIEW user setup, drivers are kept on the National Instruments website. You can usually just set up for the scope's model number, and this will bring up the drivers if they are available. IV6 class drivers are also pretty common, but these are usually available from the scope's manufacturer's website. Our probe design engineers like to say that an oscilloscope is just a display for probes. I'm sure that doesn't impress many of the scope engineers on this call, but the fact remains that probes are a critical part of the system. Check the probing alternatives for any scopes you're considering. In today's scopes, the instruments and probes can communicate with each other. This allows the scopes not only to sense the right scale factors, but it also allows to change the attenuation factors or ranges on the scope's front panel. The scopes can tell you the right on the screen when a probe draw is open, and it can guide you through procedures like current probe degaussing. Let's spend a little bit of time with updating you what's new at Tektronix. The TPS 2000 series of oscilloscope is the next generation in basic oscilloscopes. It has many first and best-in-class features and functions. Firstly, it has the longest record length of any basic oscilloscope in its class at 20 million points. It also has the first and biggest 9-inch WVGA display with 15 horizontal divisions, as well as 10 vertical divisions to allow 50% more signal viewing. You can easily, confidently analyze signals with up to 32 automatic measurements. It is also the only basic oscilloscope in its class to have Tech VPI interface for better, more accurate application coverage and measurement. It is also the only basic scope in the industry with both a 5-year standard factory warranty and a total protection plan available. All of this is available starting at $1,200. The second thing that is new at Tektronix is a new product introduction around of the IsoVu Measurement System. What is that? Simply, whether you're designing an inverter, optimizing a power supply, or testing communication links, measuring across a current shunt resistor or debugging EMI, ESD issues, common mode interference has caused engineers to design, debug, and evaluate, as well as optimize in a blind way. Revolutionary IsoVu technology uses optical communication and power over fiber to complete galvanic isolation. When you combine an oscilloscope equipped with a Tech VPI interface, it is the first and only measurement system capable of accurately resolving high-frequency bandwidth, differentiated signals, and in the presence of large common mode voltage. Utilizing this electro-optical sensor is to convert the input signal to optical modulation and allowing common mode rejection ratios of 1,000,000 to 1 at 100 megahertz. So apart from being the only system with complete optical isolation and high common mode rejection, it also combines at a 1 gigahertz bandwidth at 2,000 volt common mode voltage range and 50 volts differential voltage measurements. This is the only system on the market that allows all of these within of one solution. We have a rich archive of resources available at the general information link at the bottom of the slide, and a more detailed white paper on how the system works and on other VGS measurement techniques on wideband gap semiconductors. That's all the time that we have today. I know that we have covered quite a lot, but it is my earnest hope that you're leaving knowing a little bit more than when you started in the session. We'll now take some questions from the audience. We had a few come in during the presentation, and we'll take those first, but please feel free to keep asking questions. And thank you so much for attending.